Hello, we are the Mathletes, and we chose to do our project about genetics. In order to prove that little q equals 1/2 big Q plus big R, we first set up a Punnett square. Using the Punnett square, we were able to identify that 2 out of the 4 genotypes were heterozygous, so we plugged this number in for capital case Q. We also did the same for capital case R and identified that 2 out of the 4 genotypes were heterozygous recessive. Using these numbers, we were able to solve for little q and got that it was equal to 3/4. This correlates to the frequency of little a alleles seen in the Punnett square, where 6 out of the 8 alleles are little a. We took the same approach for finding the frequency of big A and used the equation for little p and got that it was equal to 3/4. This again correlates to the frequency seen in the Punnett squares, where again 6 out of the 8 alleles were big A. In order to prove that p squared plus 2pq plus q squared equals 1, we used the previous equations and added them together because we were given that p plus q equals 1. Using the two equations and substituting p squared for p, since those represent the frequency of heterozygous dominant, and substituting q, or uppercase Q, for pq, since that is representative of the heterozygous genotype, and substituting r for q squared, since that's representative of the homozygous recessive dominant, we were able to justify that pq plus 2pq plus q squared equals 1. Moving forward, using the equation fp equals 0.8 p squared plus 1 times 2pq plus 0.2 q squared, we were able to identify the frequency of the dominant allele. We are able to do this because we are given that p plus q equals 1. We can rearrange that equation so that we have p equals 1 minus q. And then using the square root of the q squared value given in the equation, we were able to plug in that number to find the frequency of the dominant allele. In this equation, we see that there is going to be different frequencies of genotypes that are not 100%. This is due to the heterozygous advantage present. Since there's a heterozygous advantage present, the homozygous genes are not going to display 100% fitness, and therefore this disrupts the Hardy-Weinberg equilibrium, which causes the change in allele frequencies. Next, we were able to use the balance equation to find the maximum value of the heterozygous frequency. To do this, we substituted 1 times 2pq for f of p. We also were able to rearrange p plus q equals 1 to q equals p minus 1 to substitute for the q value. By rearranging the equation, we were able to prove that f of p is equal to 1 minus 0.2 p squared minus 0.11 minus p squared. After proving this equation, we set up the derivative and set it equal to 0. By solving for the derivative when the value is equal to 0, we were able to find that at 4/5 frequency of p, there is the maximum heterozygous frequency. So f of p is the frequency of the heterozygous genotype in this equation. The value we calculated above is telling us that the value for which the frequency is at its maximum. This is general heterozygous advantage over the other genotypes. Another way to find the maximum value for P when the heterozygous genotype is at its highest frequency, we can use 1 plus S1 P squared plus 2 PQ plus 1 plus S squared, or S2 Q squared. By setting this by finding the derivative of this equation and then setting it equal to 0, we are able to find the maximum value of the heterozygous genotype frequency. Since both values are negative values, the frequency of the heterozygous genotype will have to be greater to make up for this fact. Therefore, it is representative that the heterozygous genotype has its highest frequency at this specific point. Moving forward, we are able to solve for using the given equation for P1. The equation Fp0 equals 1 plus S1 P0 squared plus S2 1 minus P0 squared can be used to find this value. First, by rearranging this equation and plugging back in P0, we are able to identify the P, Q, and R values. To find the frequency of P1, we have to get the frequency of P over the total amount, or we have to get the number of P alleles over the total amount of alleles. We can do this using the equations found above in the previous questions and then substituting the following numbers for each variable. By doing this, we are able to solve for P1. This is the conclusion to our presentation. Thank you so much for watching.